I'm just testing my slides. Let me know if you need anything at any point.
No problem. I'm just making sure the audio is perfectly fine. Could someone speak real quick?
Test 1 2 3. Test 1 2 3.
Okay, let me turn up your audio just a
Test
bit.
1 2 3 4 5 6 7
Um,
10.
and also,
ABC.
Rob, can you speak like maybe like as loudly as you think you would during
One,
the?
yeah, this is the normal volume I would like to use.
Okay.
If it's too low,
Oh no,
I
it's
oh,
perfect. I'm just
okay.
adjusting levels.
Okay. All right.
Turn up
I'm
your
just
audio just a bit.
double checking that nothing's off on my end.
Hello, and welcome back to the Mechanochemistry discussions. This seminar series is hosted by the NSF-funded Center for Mechanical Control of Chemistry, or the CMCC. The goal of the seminar series is, as always, to bring the community together. Our seminars stream live on the third Thursday of every month at 11 a.m. Eastern and are available to watch anytime on the YouTube channel. The YouTube channel is home to all of the excellent presentations we've had so far as part of the seminar series, and I encourage you to check them out. We also hope that you will join us for our upcoming seminar series speakers in the few months ahead. Before we get started, a great big thanks to a few people. First, Dr. James Batiste, the Center Director, Jennifer Belsick, the Center's Administrative Coordinator, and two CMCC students who assist greatly with the seminar series, Quintarius Moore and Katie Floyd. Thank you so much for joining us. Please do follow our YouTube channel for the CMCC Mechanochemistry discussions, as well as following us on Twitter. Lastly, a few quick guidelines. Reminder that the seminar is being recorded. If you have questions, please do send them to us. You may either type them into the YouTube channel, or you can email them to us at cmccdiscussions@gmail.com. Either way, they will be propagated to the speaker at the end of the presentation. And now it's my great pleasure to introduce my friend and colleague at the CMCC, Dr. Robert Carpick. Dr. Carpick is the John Henry Town Professor of Mechanical Engineering and Applied Mechanics at the University of Pennsylvania in Philadelphia. He studies nanotribology, nanomechanics, and scanning probes. He is a recipient of the AVS Nanotechnology Recognition Award, the ASME Newkirk Award, a R&D 100 Award, and an NSF Career Award. He's a fellow of the ASME, the American Physical Society, the Materials Research Society, the AVS, as well as the Society of Tribologists and Lubrication Engineers. Dr. Carpick holds 10 patents and has authored over 200 peer-reviewed publications. Before joining UPenn in 2007, Dr. Carpick was a faculty member at the University of Wisconsin-Madison. He received his bachelor's from the University of Toronto and his PhD from the University of California, Berkeley, both in physics, and was a postdoctoral researcher at the Sandia National Laboratory. He served as department chair at UPenn from 2011 to 2019, and since 2020 has served as the Director of Diversity, Equity, and Inclusion for his department. Please join me in welcoming Dr. Carpick to the Mechanochemistry discussions.
All right, hello everybody. Thank you very much for joining, and I'd like to thank the Center for the Mechanical Control of Chemistry for organizing this series and for the invitation to speak to you today. I'm going to talk to you about research performed in my laboratory by former graduate student Lu Fang, who's now at Tesla. And this was done in collaboration with ExxonMobil, Spiridon Chorus, and Martin Webster, formerly at ExxonMobil, and now an adjunct professor at Penn, has been involved. And I will also include some work and as well as background information from James Batiste, who we are collaborating with on this work. This was funded by the National Science Foundation as well as by ExxonMobil. For those of you who are new to mechanochemistry, there may be people joining who are not experts and who are curious to learn. I'm going to give a very quick high-level overview. Mechanochemistry has been around since antiquity. The mortar and pestle is a famous example. It's not just compacting materials together, but it causes chemical reactions to occur. Whether it's dry powders or liquids, you can cause chemical reactions to occur by applying tension forces, compression forces, shear forces on molecules, and that can lead to chemical transformations. This is manifested all throughout nature, through science and engineering. Mechanotransduction, the way the sense of touch works, actually involves a transformation from force to chemical stimulus. The study of tribology, friction and wear and adhesion and lubrication, involves many times chemical reactions that occur that are induced by forces and that then affect subsequent friction and wear behavior. In food processing, milling, shearing, shaking of foods often is, again, not just breaking things up into smaller particles, but actually causing chemical changes that can be beneficial. And then finally, and perhaps the biggest economic impact is through chemical synthesis. Mechanochemistry is used currently for synthesizing molecules, but as I will indicate to you, its potential is not yet fully tapped. There's all sorts of potential to really transform the sustainability and the power of chemical synthesis by using and better understanding mechanochemistry. And so mechanochemistry has been recognized very recently in chemistry world in 2019. I reported that the International Union of Pure and Applied Chemists had named mechanochemistry as one of 10 innovations, chemistry innovations that will change the world. Key reasons: it can make possible processes that are hard to do, maybe even impossible to do by regular solution synthesis. It also can permit reactions to occur without the need of a solvent or for minimal amounts of solvent, which is such a massive contributor to waste. And so that potentially can be reduced if we could greatly increase the amount of reactions that are used that harness mechanochemistry. But as noted in this article, scientists are still struggling to understand how the process works on a molecular scale. So there's a lack of fundamental understanding, and there's been a lot of progress. There are models, there are some impressive advances, but at this point, we really don't have the tools to predict or even to measure the forces that are occurring that cause chemical transformations in a general way. There are some beautiful specific experiments using atomic force microscopy to pull on molecules using controlled forces and stresses. I'm going to tell you today about work we've done to try to expand our ability to understand the forces and the stresses that are acting on molecules that lead to mechanochemical reactions. So that's a key challenge. And why do we care? There's all sorts of payoffs. Mechanochemistry really can address pretty much all of these 12 principles of green chemistry that have been laid out. Like I mentioned, you can do reactions solvent-free. Mechanochemistry can be much faster in causing reactions to occur and in synthesizing materials. You can increase the yield depending on the reaction. You can also increase selectivity by controlling conditions. Force is a new variable that allows you to direct the chemical pathways potentially toward directions you seek. Mechanochemical reactions can also consume less energy because you don't necessarily need to work at high temperatures, and you may be able to, again, do it faster and thus consume less energy in the process. And reactions can be done without producing undesirable side products. So all of these advantages really give all sorts of motivation for wanting to advance our ability to use mechanochemistry. If you look at some of the tools of the trade, these aren't all of them, but you will often see, and this is from a nice review by Mack and Anderson in the Green Chemistry Journal, you've got things like shaker mills, planetary mills, twin screw extruders, acoustic mixers, and then just things like ultrasonication using diamond anvil cells. Our collaborator Dana Friedman and Alison Altman use these methods, large volume presses to cause transformations, or just applying pressure to a liquid, just creating hydrostatic pressure by pressurizing a liquid solvent that has molecules in it. You can see reactions occur. So these are powerful tools, and people have used them successfully to synthesize all sorts of interesting molecules and products. But again, it's very hard to know what are the forces and or the stresses acting on the molecules that drive the reaction. And so here's just a movie of a ball mill in action. So take a look. At first, it'll be very fast, and at the end, we'll slow down, and you'll see what's happening. I'll turn the volume down a little bit on that. So you can see this high-speed video. You can see this ball knocking back and forth. So as it makes impact, it's crushing powders that are causing them to react. But how much force is there between the ball and the wall that it's hitting? Is it coming directly in at normal incidence? There can be a lateral velocity, so there can be some sliding. What is the stress state that occurs when those contacts occur? Those things are very hard to know. So the big grand challenge we want to try to address is to see if we can make mechanochemistry predictable. And so I'm part of a team that's led by James Batias, who I mentioned at the beginning, of the NSF Center for the Mechanical Control of Chemistry, who's the sponsor of this mechanochemistry discussion series. Our goal is to try to transform mechanochemistry so that it can be used in a widespread way, and that would have the potential to make chemistry massively more sustainable. So we have a multi-scale approach. We're doing experiments under controlled conditions in actual reactors, but often with novel in situ tools and measurement tools to determine what's going on more precisely and more exactly. We're doing mesoscale measurements where we can have a look at single contact points and characterize the stresses and forces acting and the rates of reaction. We're doing nanoscale measurements and models to try to understand how things like the interaction potential, the conditions, the temperature, the mechanical properties of the materials, their diffusivity, how does this affect reactivity? And we're working with atomic scale modeling, including ab initio simulations and calculations to look at how the energy barriers change as forces are applied. So you can learn more about the center here, also from the YouTube site. But again, one last comment for those of you who are perhaps new, or even for those veterans of mechanochemistry, I would love to encourage you to take a look at this Google Arts and Culture online exhibit that we produced in collaboration with the Science History Institute, curated by SHI's Roger Turner. This is called Mechanochemistry, the Science of Crush. It goes through the history and current practice of mechanochemistry, and we invite you to check it out. So that's a quick introduction to our center and the potential for mechanochemistry, and this challenge of trying to understand what is happening when contacts are made and forces applied to cause mechanochemistry. So the approach that we've taken in our lab is to do some instrumentation development and apply it to a particular system, one so far, but more to come, where we try to apply controlled stresses and temperature to track and understand the factors governing mechanochemical reactions. So let me tell you about the particular mechanochemical system that we've looked at. But I want to emphasize the technique I'm going to show you can be applied to many other systems. So the particular molecule that we've looked at is called ZDDP. It's zinc dialkyldithiophosphate. This is its structure. It's this organometallic molecule that's been around for a long time. It was developed as an antioxidant that is, it's soluble in oil due to these alkyl groups. And it's used in lubricants. And what it tends to do is react with sliding surfaces. So for example, there are very high stresses at the contact between the piston rings and the cylinder walls in an internal combustion engine, among many other contact points in the engine. These would wear out even with a very good lubricant in place. You need these molecules added to the oil to prevent wear and damage of the steel components. And if you look at what's happening, and this was realized some time ago, the sliding surfaces, you have a lubricant film in between, but the solids make contact with each other sometimes. At high stresses, high temperatures, you can get this solid-solid contact where the lubricant has been squeezed out. But that's where ZDDP comes to the rescue. This molecule is very mechanochemically active. When it experiences this combination of compression and shear at these sliding contact points, it breaks down and it forms a film that coats the surfaces of the steel. And so this is really the product of the reaction, this solid film bound to the steel surfaces that protects them from wear. That film, when it might get damaged itself, but it can heal. More ZDDP from the solution can reabsorb and react and reform this rehealable film that protects the surfaces. This has been known for a long time to work. It's used in every commercial engine oil today on the market, but it does have some limitations. It's got sulfur and phosphorus in it, and that can lead to degradation of the catalytic converter, which raises concerns for energy emissions. It actually increases the friction a little bit, protects against wear, which you need, but a little more energy dissipation because of it. It doesn't work at lower temperatures. You need at least 50 degrees C, and you need some sliding. It doesn't work with pure rolling. Also, if conditions get too harsh, very high stresses or other effects like electric fields can cause the wear-resistant behavior to not function well. So while it's great for engines, there are many applications like electric vehicles, like wind turbines, or just using low viscosity lubricants, which would save a lot of energy because of their lower viscosity, but the conditions are too harsh and the ZDDP no longer works. It also doesn't work as well on lightweight alloys that are desired for replacing things like steel. On lightweight aluminum alloys, for example, it's not effective at forming these antiwear films. So this is a tribology motivation for trying to come up with alternatives. And in order to do that rationally, there's been a desire in the tribology community to understand how ZDDP works so that we can design ways to reduce and replace it with some other more effective antiwear additive. Let me quickly show you a bit of a sort of a high-level simplified overview of the chemistry, the tribochemistry of this molecule. You've got the zinc coordinated by sulfur, these phosphorus groups, and then through oxygen linkages, the alkyl groups. There's some thermal decomposition that typically happens because there's heat in the engine, maybe some heat from frictional sliding as well. And then these decomposed products can undergo an exchange reaction where the alkyl groups will be transferred from oxygen sites to sulfur sites. So you now have this configuration, and now you've got these oxygen groups available to react with others. And what happens is that these phosphate groups react very favorably with each other and very rapidly. And so this is understood to be a low barrier reaction, a very favorable reaction that leads to this essentially cross-linking that forms a long chains of these phosphorus groups that form a solid-like film. So it's basically a phosphate glass that forms on the surfaces. Here's a cross-sectional TEM micrograph showing an iron oxide surface, and then this tribofilm, this phosphate glass film that's grown on top of it. Mostly it's phosphorus and oxygen. There's still some sulfur in there. There's some iron mixed in often. There's maybe still some of the hydrocarbons mixed in. But it's a solid, and it is able to grow to a thickness of a few hundred nanometers or so. It has a graded and rather complex chemical structure. It also has quite a bit of morphology to it. It's rather patchy. And there are long stories into understanding all of these. I want to simplify this for the purpose of this talk and just emphasize that this set of reactions from the native molecule, precursor molecule, all the way to this phosphate glass is something that is greatly accelerated when there are mechanical forces present. And that's what we'd like to understand. So there's a very nice review article from a few years ago, but it captures a lot of the research up to this point by Hugh Spikes at Imperial College, who has studied this molecule and a lot of other aspects of tribology for many years. So we have this motivation to understand this molecule's mechanochemistry. And up until about 2010, there was a lot of debate about what exactly how was it that stress was causing this reaction to occur. Some very nice simulations done in 2010 by Martin Muser and coworkers showed that one way in which stress can affect the mechanochemistry is by inducing cross-linking between the phosphate molecules. So they did some density functional theory showing that applied pressure can cause cross-linking to occur, some of which is reversible when pressure is released, but some of it is irreversible. They found a threshold of several gigapascals. That's quite a bit of stress that was required to cause this cross-linking to occur. And that suggests that, well, that's why you need a hard material like steel as your substrate to see this film building up. It needs to withstand this applied pressure. If you have a soft material like these aluminum alloys, they're not as hard as steel. They won't sustain as much pressure when they make contact. And so therefore you may not get as much cross-linking. You won't get as strong a film. So that's one mechanochemical aspect that's where there's some support, some strong support for it. More recently, around 2015, our group, in collaboration with ExxonMobil, did some work using atomic force microscopy, where we would slide a nanoscale tip in a small area on an iron surface inside of an oil that contains this molecule. And we tracked how fast that tribofilm grew because of the sliding between our tip and the substrate. And we saw that there was pretty much an exponential increase in the rate of growth of this tribofilm in these nanoscale experiments. So this is the growth rate as a function of how hard we're pressing with our tip. We also see an acceleration with temperature. And this is, of course, reminiscent of the Arrhenius rate law. The rate of reaction, or in this case, the rate of growth of the film, is some constant times e to the minus energy barrier over kT. So that would explain the thermal effect. The stress effect, as many people in mechanochemistry know, can be described by this Eyring-like model, where you have a linear dependence on stress multiplied by an activation volume. And I'll explain more about this in a few minutes. But the key is the application of stress reduces the energy barrier. And a few years later, or a year later, Hugh Spikes' group showed that they could vary the shear stress that they're applying to a liquid and measure the rate of growth. And this was a macro scale, not a nanoscale experiment. And they could see that the dependence, and this is a log scale here on the y-axis, it followed a nice linear dependence. And that suggested that the stress component that was actually causing the tribochemical reaction to occur was a shear stress, not a normal stress. So shear stresses you get when you have shearing, of course, sliding, or just a lateral displacement between two planes. Compressive stresses or hydrostatic stresses you get when you're compressing uniformly in all three directions. You can also compress along one axis, get uniaxial compression. But you can think about stresses in these two ways. Any stress state that is due to a combination of forces can be described as the sum of a certain amount of hydrostatic pressure, either in compression or tension, and a certain amount of shear, or what we sometimes call in the mechanics world deviatoric stresses. So really, those are the two elements of any generic stress state. So we set out to try to figure out a way to independently verify the hydrostatic stress and the shear stress to see if we could separate them and understand which one is contributing or how much each is contributing. So the instrument that Hugh Spikes used for his study and that we have used is this thing called the mini traction machine. It's a nice convenient desktop instrument made by PCS Instruments in the UK. It's used widely in the tribology world. What you've got is this mechanism inside this box that is applying forces to a contact inside this cell. Inside this cell, there is a pot that holds the lubricant oil. You have a disc that rotates, and then you have another ball that independently rotates. And so you have a contact between this ball and this disc. So if we look at a side view, here's that lubricant bath. There's a heater, so we can control its temperature up to about 150 degrees or so. The ball makes contact with the disc, and they are each being rotated at independent rates. So you can control those such that you can have pure rolling. You could have one of them stationary and the other moving, so you have pure sliding. Or you can have them rotating at different rates, so you get a mixture of sliding and rolling. That's important in tribology because it lets you simulate and measure different conditions that are relevant for components. But as you'll see, it's also useful for the experiments we're about to show you. You can control the normal force that you apply. And then, depending on the properties of the lubricant, you get a certain amount of shear force generated. So typically, you apply a normal force, you get a friction coefficient, or what we sometimes call a traction coefficient, times that normal force, and that gives you your shear force. So in this normal configuration, we're just we're controlling the normal force, we're controlling rates, but we're not necessarily controlling the shear force. We just get what we get depending on the conditions. But we are getting both. We're getting a hydrostatic pressure inside the solution. We're getting a shear stress inside the solution. And if we put molecules that are soluble inside this oil, then what we've got is essentially a reaction cell. So there is a hydrocarbon fluid that separates these two surfaces because of hydrodynamic lift. it is under very high, it can go up to very high pressures, and you can apply very high shear stresses by using high shear rates and high viscosities. And so this molecule or molecules you have in there are now being subject to compressive stress, shear stress, all at the temperature you want. This is the well-known phenomenon as hydrodynamic lubrication. This is what keeps machines from breaking down when you add oil to them. It's this film that's sustaining pressure and shear. And let me quickly show you a video of this instrument operating so that you can have a sense of it. So I hope you can see this alternate video now. So here's you can see the ball rotating and now the disc rotating inside this fluid. Okay, so that's the standard experiment. Okay. All right, so to go back. All right, hopefully my PowerPoint is back. All right, so I told you that we've got a ball and a disc, but we want to measure the product. And the way we do that is using a technique that PCS provides called spacer layer imaging. So we use interferometry to measure the amount of this tribofilm that's built up on the ball. So the way this works is to periodically lift the ball up and press it against the window that leads to the camera. So here's the case where you're running it in contact, and then you periodically stop the experiment, lift the ball up, press it against this window, and this camera measures the intensity of light reflected back. And by the fact that there's this little semi-reflective spacer layer here, you get an interference effect that will depend on the thickness of this film. Okay, so we rotate the ball and disc. They're made out of tungsten carbide, so we can apply high forces, and we periodically load it against the window. And then we go back and repeat the process. More cycles of reacting, and then once again measure how much product we have. So we can build up a measurement of how much reaction has occurred by measuring the thickness of the film on the surface of the ball. So here's an example. This is a movie showing a series of frames obtained through this periodic imaging using the SLIM technique. So this will cycle through. You can see the contact between the ball and the window. It starts off with nothing, it's flat, but then you see these different colors, and that's this strip of tribofilm that is built up because of the mechanochemical reactions occurring in this reaction cell. The temperature, the applied pressure, the applied shear causes reactions to occur. They bind to the surface and they build up a film. We can convert this color map into a thickness and therefore measure the thickness and the volume of this tribofilm as a function of time and get reaction kinetics from it. So that's all great, but we're still lacking the ability to independently control pressure and shear stress. We'd like to vary those. And so for those of you not familiar with tribology, don't be afraid. I'll summarize this at a high level, but a key aspect of tribology and of hydrodynamic lubrication is that there are different lubrication regimes. If you're sliding very fast in a high viscosity fluid and your load isn't too low, you'll get a nice hydrodynamic film separating your surfaces. If you start increasing the load or reducing your sliding speed or reducing your viscosity, you don't get as much lift. The surfaces start to press together, and this is called the mixed regime. You get some lubricated separation, but some contact. And then finally, you get what's called boundary lubrication, boundary contact. This is for sort of nominally smooth parallel surfaces. When you have a ball on a disc, where, in other words, where the contacts are non-conforming, this is called elasto-hydrodynamic lubrication. Okay? There are very high stresses that cause elastic deformation of the ball and the disc. You get an exponential increase in the viscosity of the oil because of that high pressure. And essentially, you can get still a very nice film under high pressure, but to make sure you don't get contact, you have to keep the roughness small. So there's roughness to these surfaces. I call this sigma, the RMS roughness of the two surfaces. So as long as that oil film thickness H divided by the mean square roughness of the two surfaces is bigger than about 3, we can be confident that there's no surface contact. We can make this H big by using highly viscous fluids, by sliding sufficiently fast, by not using loads that are too high. Okay, so as long as we have a fluid that does that, we're happy. So we can take our fluid and mix in some ZDDP, and that gives us something where we can test this. But we can do something else, and that is we can change the composition of this fluid that we're pressurizing. And so what we did was to have a mixture at different ratios of a high traction fluid, so a very highly viscous material called polyisobutylene liquid, with a lower traction fluid, a lower viscosity fluid, polyalpha olefin. We can mix these in different ratios, and because they have these different viscosities, and thus different amounts of traction that you measure as a function of that slide to roll ratio, we can control how much shear stress we get. So imagine if this is just polyalpha olefin, it's got low traction as you change your slide to roll ratio between the ball and the disc. The polyisobutylene has quite a bit more. If we mix these together, we get a combination of them. So here's the traction that we get for different slide to roll ratios for a range of mixtures. At the top, 99% of this high viscosity polyisobutylene. At the bottom, it's 54% polyisobutylene, the balance being the polyalpha olefin, low traction fluid, and then ZDDP. So you can see that we've got independent control of the traction coefficient at a given slide to roll ratio. We're not changing the temperature, we're not changing the load, but we can change the friction, the traction coefficient, and thus the shear stress in the fluid by changing the composition. So we choose a slide to roll ratio of 6%. That's where we get close to a maximum value of this traction coefficient. So very good contrast, a nice range of values without some other undesirable effects that can happen at high slide to roll ratios. So here's an example. If I go at 140 degrees C, here's a series of shear stresses that I get on the vertical axis, all at the same applied load, but using all of these different mixtures. So each one of these requires the student to, the hardworking graduate student, to make different mixtures and run different tests for each one. But with a given mixture, you can vary the load. So here's changing the compressive stress for a high traction fluid, and in dark red, and then here in blue, here's changing the mixture. Here's changing the load for a mixture that has low traction. So I've got different values of stress, all shear stress, all at the same compression. I double check, yes, I've got a nice thick film, so there's no surface contact here. I'm in that elastohydrodynamic condition. And so just to make it very clear, we're rotating this disc. If we're in this 99% polyisobutylene mixture at this temperature, if we apply 2.5 gigapascals of compression, we get 260 megapascals of shear. If we change the composition and do a separate test with this low traction measurement, now we've dropped the shear stress to 155 megapascals while keeping everything else the same. All right. So that allows us to do a test of different shear stresses, but we can also vary the compressive stress. So here I had this vertical box. Now, as you can see, I've got a horizontal box. It's not perfect, but what I can do is choose the right mixture so that I can keep the shear stress approximately the same while I'm varying the compressive stress. So I can apply 2.5 gigapascals with this mixture and get close to 200 megapascals of shear. And then I can switch to this other mixture, still apply a different compressive stress, but maintain the shear stress at nearly the same value. So now I'm varying my shear stress along the horizontal axis. Okay, so this is what we've dubbed the stress-controlled mechanochemical reactor. We can control that hydrostatic pressure, we can control the shear stress, and we can do it all at different temperatures. So again, I showed this before. Once again, we do this at a given set of conditions and watch the film build up. Play that again. And this gives us the kinetics of the reaction. And we focus on, by measuring both the width and the thickness, we can get the volume of product. And we focus on, the early stage growth before it starts to level off. Okay. So if we look at a function of normal stress, a function of shear stress at a fixed normal stress, you can see here is the kinetics of growth at the slightly lower pressure shear stress, I should say, of about 235 megapascals. And then up here in darker brown, we have about 260 megapascals of shear. You can see there's a clear difference, and we zoom in at the early stage. There's a little run-in period. We think it's cleaning off of contaminants or maybe oxides. And then you see a clean growth curve that's very different for our two different shear stresses. So that allows us to put data points on this plot of kinetics of growth versus shear stress. And sure enough, we see there's a pretty rapid acceleration of the mechanochemical reaction as we increase the applied shear while keeping everything else constant. We do the same thing for the we do two different conditions here. I just showed you this set of data, which is at 140 degrees C. We redo it at 100 degrees C, so we get two different temperatures. And from that, we can fit this I-ring model that I showed before. So again, the activation barrier being modified by the applied shear stress through an activation volume. We can also follow this as a function of temperature. So here's a series of 5 different temperatures, all for these different blends, so different shear stresses, okay? And from that, we can pick experiments where we kept the shear stress the same, kept the compressive stress the same, but had different temperatures. And from that, again, we see a rapid acceleration of the mechanochemical reaction rate with temperature. It follows Arrhenius kinetics nicely. And I'll show you the fits in a minute. Sorry, I don't have them on this slide. But we've done this for 2 different shear stresses, and I'll show you in a minute how it fits to, again, this I-ring model that includes the effective shear. And then finally, we can vary the compressive stress. So pick a shear stress and vary how much compression we're applying, all at the same temperature. And here's where we see a big surprise. Compressive stress does not accelerate the growth. It actually slows it down. So the higher our compressive stress over this region, the markedly slower the volume of the tribofilm is. And this is observed at 2 different temperatures, which have nearly similar shear stresses. So we cannot describe this by just including shear stress. That's only one stress component, like I said earlier. We need to consider how the compressive stress is affecting the reaction so that we can describe it with a model and how it inhibits the growth of ZDDP. So let's just remind ourselves of the 2 different forms of the I-ring model that have been we considered earlier. We have the shear stress reducing the barrier. We could have the normal stress reducing the barrier, or I should say the hydrostatic compressive stress. But there's this extended I-ring model, and that's been out there for a while. We didn't come up with this, and this is nicely reviewed in Hugh Spike's review article in 2018 in the journal Friction. You include both. You have a shear stress altering the activation energy, and you have the hydrostatic pressure modifying the activation barrier. And what you have are 2 different activation volumes, delta V for shear, delta omega for pressure. Okay. The sign here is flipped. That's I'm not pulling a trick here. This is just because it's a compressive stress. So in mechanics world, that's really negative. Compression is negative. So we're going to make P a positive value, and we'll just take care of the fact that it's a negative compressive stress by putting a plus sign here. Okay. But the activation volume itself, that can change sign. Here's a simplified, we'll call it a first order description of activation volume. And I'll warn you, it's not correct. I'll show you the correction in a moment. But first, here's the simple form of it. You have reactants, you have a transition state, you have a product. You can define this activation volume as the volume difference between the transition state and the reactants. So if I'm cleaving bonds, you would expect that the transition state has a larger size than the reactants. And so that would be a positive activation volume. If you were forming bonds, you would expect that the volume of the reactants is lower of the transition state is lower than the reactants. So you would have a negative activation volume. Okay, let's think about a bond cleaving reaction. If we're cleaving bonds, and if what we're doing is having molecules that are in a shear flow, and that shear flow is acting, at the top of the molecule, it's going to the left, the bottom of the molecule is going to the right, that can have the effect of breaking bonds. So shear stress, if it's a bond cleavage reaction, you could imagine would lower the activation barrier. And indeed, if delta V is positive, and I've got this minus sign in my exponential here, indeed, delta U minus shear stress delta V, that's going to lower the activation barrier. By the same token, though, compressive pressure is pushing molecules together. That would tend to inhibit the tendency to cleave bonds. So this term plus delta V, again, activation volume is positive, but compressive pressure by pushing molecules together inhibits the tendency to cleave bonds. So this is suggestive of the way in which shear and compression inside this fluid can act in different ways if what we're dealing with is a bond breaking reaction. Now, this definition of activation volume is inadequate. It does not work. It works for some cases, but it's been shown by many others that it can fall short. And the way I like to think about activation volume is that it's not just a physical volume. You can think about it as essentially a Taylor expansion of the activation energy. The first term, if I do a Taylor expansion about, say, shear stress, would be that shear stress times the first derivative of the activation energy. And then you'll have a second order term, the second derivative of the activation energy, and so on, okay? So this coefficient here on the shear stress, that's our activation volume. It's really the rate of change of the activation energy with applied pressure or stress. So let's use this extended I-ring model with these two different activation volumes and see if it works. And actually it fits the data rather well. So here's the dependence of growth rate on shear stress for two different temperatures. Here's the dependence of growth rate on temperature for two different shear stresses. And here's the dependence of growth rate on the compressive stress at two different temperatures. Again, you see that inhibition of the reaction with compressive stress. From fitting all these together, we can get an activation barrier. It comes out to be about 0.54 EVs. That's quite reasonable for a covalent bond modification or bond breaking reaction. And we get activation volumes. The activation volume for shear is about 0.18 cubic nanometers. The activation volume for compression is more than an order of magnitude smaller. So although there's inhibition of the reaction by compression, it's a weaker effect than the acceleration that you get due to shear. So shear is quite effective with this molecule in promoting the growth. And while the compressive stresses are high, that activation volume, the sensitivity to compression, is not strong enough to prevent things from happening. So we get a stronger effect from the shear, and it clearly dominates the compressive stress effect. So what we've learned from this is that we can use different compositions of fluid to control the amount of shear stress we get when we choose certain values, specific values of temperature and compressive stress. From this, we could have a range of values of stresses. And from that, we could show that this extended I-ring model does a good job. And that's consistent with the idea that it's a bond breaking reaction. Shear is helping pull the molecule apart. Compression is acting against that, but it's a weaker effect. I can jump here. The question then is, what is that mechanism by which compression inhibits tribofilm growth? Well, certainly you can imagine that the probability of bond breaking may get lower as compressive stress increases. There is in this process bonds that form between the sulfur and the zinc, and that would be part of an adsorption process on the surface. That those bonds need to break so that adsorption to the surface can occur. So that sulfur zinc bond in the molecule it may be being assisted by the shear, but inhibited by the compression. There could also be bond breaking between the oxygen or sulfur containing groups and the alkyl groups that are on this molecule. And the latter is indeed believed from other studies to be the rate limiting step. So we think that this could be a key aspect, and I'll go into this more in one more slide. It's also possible that compressive stress is reducing the mobility of the ZDDP molecules. You've got much higher stress in the contact zone, and that's going to inhibit diffusion. That reduced diffusion could reduce the reaction rates. We've done a back of the envelope calculation, and we found that the rate at which the diffusion of ZDDP changes is not sufficient to explain the reduction that we've seen in the reactivity with compression. So we think this may have a contributing factor, but it's not the dominant one. Finally, Le Chatelier's principle would tell you that the dynamic equilibrium simply gets shifted under compressive pressure. That perturbs the reaction, and that could be a way to think about the effect of compressive stress. But let's take a look at the reactions I showed you before. Again, skipping a couple of the steps, a key aspect is this oxygen-sulfur exchange that happens at elevated temperature, leading to these phosphate groups being available to form a glass. If that is being promoted by shear, essentially breaking the bond between the alkyl and the oxygen, and then a subsequent formation of the bond between the alkyl and the sulfur, that initial bond breaking might be the key. And like I mentioned earlier, work by others has suggested that that is indeed the rate limiting step. And as I mentioned before, once you get to this point, this is a very rapid spontaneous reaction to cross-link and form the phosphate glass. So our suspicion is that it's this bond breaking that the shear is promoting and that compression's inhibiting. But work needs to be done to really verify that. So what I've shown you today is that we've developed a method where we can independently control the shear stresses, compressive stresses, and temperatures. And as I mentioned earlier, this was based on work done initially in Hugh Spike's group at Imperial College, where they showed that these can affect that shear stress affects the reaction rate. Our contribution was to change the mixtures so that we can vary the compressive stress independently. We've shown that stress, shear, and temperature promote tribofilm growth. Compressive stress inhibits it. The extended Eyring model with a constant activation volume fits the data well. And it suggests that there's a bond breaking reaction as the rate limiting step in the ZDDP reaction. There could be an effect from local viscosity. There could be an effect from equilibrium being perturbed, but we lean toward this first aspect being the key. This work was recently published in Faraday Discussions, and so I invite you to have a look at it. And I invite you to ask me any questions you've got. With that, I'll stop, and thank you again for your attention, for joining. I look forward to your questions.
All right, thank you, Rob. Professor Carpick will be formal. All right, I have quite a few questions. I'll choose a few here. For the ZDDP, it seems that the phosphorus and sulfur are the most important. What role does the alkyl chain play, if any, in this process?
Right, so the alkyl chain is there to ensure that the molecule is soluble in the oil. That's the key reason for it being there. But what role does it play in the reactivity? And actually, there has been very nice work showing that if you change the specifics, the specific structure of that alkyl group, you can change the reactivity. So you can have a primary alkyl where you have just a carbon, single carbon chain coming off, but people have also synthesized, excuse me, secondary alkyls where you have a carbon bonded to the oxygen, and that carbon is bonded to two other carbons instead of a single carbon. And when you do that, that shifts the reactivity and is a little more reactive. It weakens the bond between the primary carbon and the oxygen, and you see an acceleration of the growth. The data that I showed you today was all using just a secondary alkyl group, and so it's referred to as a secondary ZDDP. People have done primary ZDDPs, and indeed, reactivity is slower. So there is an effect of the alkyl group on how readily these react, and that ultimately has an effect on the growth rate and the subsequent composition and properties of the tribofilm. And there's a I think a lot to be discovered to understand exactly how that all works.
Thank you. Another question. Very nice presentation. How do you know that the oil composition does not affect growth rate rather than the shear and normal stresses?
Oh, I see. So chemically, all of these oils are identical except for just variation. The two oils are identical. And I mean, I'm sorry, we use the same polyisobutylene for all the measurements, the same PaO for all the measurements. We're just changing the mixture. If we look at pure polyisobutylene and we look at pure polyalpha olefin, and we measure the growth rate for the same temperature, same compression, same shear stress, the growth rates are the same. So we see no change in the kinetics of growth in either of the two pure fluids. And the way we can do that, you might say, how do you keep the shear stresses the same? You can change the slide to roll ratio, or you can change the sliding speed. And both of those are ways to control the shear stresses. So yeah, under the same conditions, the ZDDP growth is unaffected. And Hugh Spikes also had shown in his work where they used a different kind of traction fluid, the growth and the composition of the ZDDP was not affected by the oil. So our claim is that the oil is just an inert carrier fluid to transduce compression and shear stress. Limitation, if you go to too high a pressure or too high a temperature, yes, those molecules, those hydrocarbons, they'll start to degrade. But these all the way down to room temperature, and you can even cool the oil. It remains liquid down to low temperatures. So by all means, this approach could be used for studying reactions that have much lower activation barriers.
All right, great, thank you. Let's do one more. This is probably a very simple question, but how does shear stress within the fluid cause a film to form on the surface?
Yep, that's a good question. So that indeed is something we aren't able to directly see. We know that the film forms. We see it here. We can measure it on the ball afterwards. It's there on the surface. We also know that we do not have solid-solid contact. We know this from the forces we measure. We know it from the very well-established elastohydrodynamic theory. We know it because we can cause surface contact, instrument down, and then we see a transition where it occurs. So we know that, yes, there's true fluid separation, yet there's product building up on the surface. We think that's because the molecule breaks down and starts forming, maybe I should show this other diagram. It breaks down, and perhaps at this stage here or here, these sulfur groups, they will readily absorb onto the surface of iron. So either at this stage or at this stage, you've got these very surface active groups, and so some fraction of the reactants will attach to the surface. Now, you might say, how do you know that that's your total yield? There could well be